settle into the sleepy mind channel. Today, we will explore the Milky Way. Before there were cities, before there were oceans, before there was even a single human thought, there was already something vast and silent stretching across the darkness of space. A great river of light, made of countless distant suns, slowly turning in the quiet. It has been there for billions of years, long before the Earth formed, long before life began, and long before anyone could look up and wonder what it was. Every star you have ever seen, every constellation you recognize, every faint point of light in the night sky, all of it belongs to this one enormous structure, the Milky Way. It is not just a collection of stars, but a vast system moving together through space, shaping everything within it. Right now, without feeling it, without seeing it, you are traveling through this galaxy at extraordinary speed. The ground beneath you feels still, the sky appears calm, yet everything is in motion. The sun is moving, the stars are moving, and the galaxy itself is slowly turning. If you enjoy journeys like this, feel free to like and subscribe, as more videos are posted weekly. There is always more to explore, and always more to understand about the universe around us. As we move further into this journey, it helps to remember that the Milky Way is not some distant object hanging beyond our reach. We are inside it, living within one small region of a structure so large that the mind has difficulty holding it all at once. Everything familiar to us, from the sun to the planets to the night sky itself, is part of this larger whole. That is what makes the Milky Way so compelling. It is both remote and immediate, both grand and personal. To understand it is not simply to learn about a galaxy in the abstract, but to understand the wider setting in which the Earth formed and in which every human life has unfolded. The more clearly we see that setting, the more the night sky changes from a backdrop into a place with structure, history, and motion. The Milky Way is the galaxy that contains our solar system, and it forms the vast cosmic environment in which every star we see in the night sky exists. When you look upward on a clear night, every visible star belongs to this single structure, even if they appear scattered across the sky. A galaxy is a gravitationally bound system, meaning everything within it is held together by gravity. It is made up of stars, clouds of gas, fine dust, and a large amount of unseen matter that cannot be directly observed. All of these components move together, forming a single system that persists over immense stretches of time. The Milky Way extends far beyond what the human eye can fully comprehend, stretching across distances so large that they must be measured using light itself. Within it, there are between 100 billion and 400 billion stars, each one contributing to the overall structure and glow of the galaxy. Our Sun is only one of these stars, and it is considered ordinary. It is not especially large or unusually bright compared to many others. This means our place within the galaxy is not central or unique in a physical sense, but part of a much larger system that surrounds us. The Milky Way is a barred spiral galaxy with a central elongated region and spiral arms that extend outward. These arms are not solid structures, but regions where stars and gas are more densely gathered, forming patterns that slowly shift over time. As these arms curve outward from the center, they create the familiar spiral shape seen in distant galaxies. This pattern is maintained by motion and gravity, allowing the galaxy to keep its form even as its individual stars move within it. This structure influences how the galaxy behaves. The spiral arms are regions where gas clouds are compressed, leading to the formation of new stars. The central region helps guide material inward, shaping the movement of stars and gas throughout the system. Over time, the galaxy continues to evolve. The arms shift, stars move within them, and the overall structure changes gradually. It may appear still from our point of view, but in reality, it is constantly in motion, quietly reshaping itself over millions of years. This opening view of the Milky Way matters because it gives us the framework for everything that follows. Once the galaxy is understood as a shaped and active system rather than a random field of stars, each later detail begins to fit into place. The number of stars, the curve of the arms, the movement of gas, and the birth of new suns all become parts of one connected picture. It also changes the way we think about our own position. We are not standing outside this great form and looking at it from a distance. We are inside it, carried along by it, and surrounded by its long history. That sense of belonging to something immense and ancient is one of the most striking things the Milky Way can offer, and it stays with us as we move deeper into its scale and design. The scale of the Milky Way is difficult to fully grasp because it exists on distances far beyond everyday experience. It stretches across about 100,000 light-years from one side to the other, forming a vast shape that contains everything we see in our night sky. To understand this size, it helps to begin with the idea of a light year. A light year is the distance that light travels in 1 year, which is about 5.88 trillion miles. Light moves faster than anything else in the universe, yet even at that speed, it would take 100,000 years to cross from one side of the Milky Way to the other. This gives a sense of how enormous the galaxy truly is. Our solar system is located about 26,000 light-years from the center of the galaxy. This places us within one of the spiral arms rather than near the core. Being positioned away from the center has important consequences, as the inner regions of the galaxy are far more crowded and energetic, with greater concentrations of stars and higher levels of radiation. In contrast, our location provides a relatively calm and stable environment. Stars are more widely spaced, and extreme events are less frequent. This quieter region may have played an important role in allowing life to develop on Earth over long periods of time without constant disruption. The main body of the Milky Way forms a disk that is about 1,000 light-years thick. This disk contains most of the galaxy's stars, gas, and dust, giving it a flattened shape when viewed from the outside. At the center of this disk is a dense bulge, filled with older stars, while far beyond it lies a much larger halo that surrounds the galaxy. When we look up at the night sky, we do not see the Milky Way from above, but from within. We are inside this disk, looking along its length. This is why the galaxy appears as a soft band of light stretching across the sky, rather than as a spiral shape. This perspective means that the light we see is the combined glow of countless distant stars. Some are relatively close, while others are so far away that their light has traveled for thousands of years before reaching us. Together, they form the pale and continuous glow that has been observed throughout human history. As technology improves, scientists continue to measure these distances with greater accuracy. By observing how stars move and how their light changes over time, they are building an increasingly detailed map of the galaxy's arrangement. In this sense, what once appeared as a simple band of light is now understood as part of a vast and complex system, one that extends far beyond what can be seen with the naked eye. Distance on this scale also changes how we think about time. Because light needs time to travel, every view into the galaxy is also a view into the past. A nearby star may be seen as it was a few years ago, while a far more distant region may be appearing to us as it was thousands of years earlier. This means the Milky Way is never presented to us all at once in a single moment. We see it piece by piece through delayed light, assembling its design from signals that have taken very different lengths of time to arrive. The galaxy therefore teaches two lessons at once. It reveals the vastness of space, and it reminds us that seeing across that vastness always means looking backward through time as well. At the heart of the Milky Way lies a region of immense gravitational power and constant activity. This central area is unlike the quieter regions where our solar system is found. It is a place where stars are packed more closely together, where motion is faster, and where the forces at work are far more intense. At the very center is a supermassive black hole known as Sagittarius, a star. This object has a mass about 4 million times greater than the Sun. It cannot be seen directly, as not even light can escape from it, yet its presence is revealed through its powerful gravitational influence. A black hole is a region of space where gravity becomes so strong that anything that comes too close cannot escape. Sagittarius. A star does not pull in everything around it, but it strongly affects the motion of nearby stars. These stars move at extremely high speeds, tracing tight and rapid paths around an invisible point. By observing these motions, scientists have been able to confirm the existence of the black hole and calculate its mass. The way these stars orbit provides clear evidence that something incredibly massive is concentrated at the center of the galaxy. The region surrounding the center is filled with dense clouds of gas and dust, along with high-energy radiation. These conditions make it one of the most energetic areas in the Milky Way. However, much of this activity is hidden from view in visible light because thick dust blocks our line of sight. To study this region, scientists rely on infrared and X-ray observations, which can pass through the dust and reveal what lies within. These observations show a crowded and dynamic environment where stars move quickly and interact more frequently than in the outer parts of the galaxy. This central region plays a crucial role in shaping the behavior of the Milky Way as a whole. Its gravitational pull helps anchor the galaxy, influencing the motion of stars across vast distances. Over time, gas and dust continue to move inward toward the center. Some of this material may be drawn closer to the black hole, while stars continue their rapid orbits around it. Although this process unfolds slowly, it contributes to the ongoing activity that defines this region. Even though we are far from the center, its presence affects the entire galaxy. It is a hidden but powerful force, quietly shaping the motion and form of everything within the Milky Way. The hidden nature of the galactic center adds to its power. We know it is there, and we know that it shapes the motion of the surrounding stars, yet much of it remains concealed behind dust unless we use specialized instruments. In a sense, the center of the Milky Way, has to be discovered rather than simply seen. This is one reason it has become so important in modern astronomy. It brings together the visible and the invisible, showing how careful measurement can reveal an unseen object of extraordinary mass. The stars racing around Sagittarius. A star act like messengers, tracing out the influence of something that cannot be viewed directly. Through them, the center becomes not a mystery beyond understanding, but a place whose reality is written into the motion of everything nearby. The Milky Way is estimated to be about 13.6 billion years old, making it one of the earliest large shapes to form in the universe. Its origins trace back to a time not long after the beginning of everything, when the universe itself was still young, dense, and filled with rapidly changing energy. The universe began with an event known as the Big Bang. This was not an explosion in space, but the rapid expansion of space itself. In the moments that followed, the universe was filled with extremely hot and dense material. As it expanded and cooled, this material began to settle and form the first simple particles. Over time, gravity began to pull matter together. Tiny variations in density caused certain regions to gather more material than others. These regions grew slowly, attracting more and more matter, eventually forming the first large arrangements, known as proto-galaxies. The Milky Way likely began as a collection of these smaller proto-galaxies. Each of these early designs contained gas, dark matter, and the beginnings of star formation. As time passed, they moved toward one another under the influence of gravity, merging together in a slow and gradual process. Each merger added more mass and complexity. Gas clouds combined, stars were redistributed, and the growing system began to take on a more organized shape. This process did not happen quickly. It unfolded over billions of years, with each stage building upon the last. As the galaxy grew, the gas within it began to collapse under gravity in more concentrated regions. These collapsing clouds gave rise to the first generations of stars. Many of these early stars were very different from the ones we see today. They were often larger, hotter, and lived much shorter lives. Because of their size, these early stars burned through their fuel quickly. When they reached the end of their lives, many of them exploded as supernovae. These explosions were powerful enough to spread newly formed elements out into the surrounding space. At the beginning of the universe, only the simplest elements existed, mainly hydrogen and helium. The heavier elements, such as carbon, oxygen, and iron, were created inside stars through nuclear processes. When those stars exploded, these elements were released into the galaxy. This process of enrichment changed everything. The gas that remained after these explosions was no longer simple. It now contained the building blocks needed for more complex forms, including planets and eventually life. As new generations of stars formed from this enriched material, they began to resemble the stars we see today. These later stars often formed with surrounding disks of gas and dust from which planets could develop. This marked a major transition in the evolution of the galaxy. Over time, the Milky Way began to take on a more defined shape. The rotation of the galaxy caused material to spread out into a flattened disk. Within this disk, patterns began to emerge, including the early formation of spiral arms. The central region of the galaxy also became more concentrated. As more matter gathered toward the center, it contributed to the formation of the dense core that we now observe. The supermassive black hole at the center likely grew during this time, increasing in mass as it absorbed surrounding material. The shape of the Milky Way today is the result of all these processes working together over immense periods of time. Mergers, star formation, and gravitational interactions all contributed to shaping the galaxy into its current form. Even now, the galaxy is not finished forming. Smaller mergers continue to occur, and new stars are still being created. The Milky Way remains an active system, evolving slowly as time passes. This long history matters because it explains how everything we see came to exist. The stars, the planets, and even the elements that make up our own bodies are all part of this ongoing story. What began as simple particles in the early universe has, over billions of years, become a vast and complex galaxy. Within it, countless stars shine, each one part of a process that started long before our sun was formed. And as this process continues, the Milky Way carries its history forward, shaping the future of everything within it. This long beginning also explains why the Milky Way contains such variety. Ancient stars, younger stars, planets, gas clouds, and dense central arrangements all exist together because the galaxy was not created in a single finished state. It grew in stages, with each era leaving behind its own traces. Some stars preserve the chemistry of the early galaxy, while later stars form from richer material and help build more complex systems around them. The Milky Way is therefore like a record written over billions of years, with older layers still present beneath newer ones. To study its age is not merely to assign a number to it, but to understand that every part of the galaxy carries some memory of the path that brought it into being. The Milky Way does not exist in isolation. It is part of a larger collection of galaxies known as the Local Group, a gravitationally bound gathering of more than 50 galaxies that move through space together. While these galaxies are separated by vast distances, they are still connected through gravity, influencing one another over long periods of time. Within this group, galaxies vary greatly in size and design. Some are large spiral galaxies like the Milky Way, while many others are much smaller dwarf galaxies. These smaller galaxies often orbit the larger ones, slowly moving around them in paths shaped by gravity. The largest galaxy in the Local Group is the Andromeda Galaxy. It is similar in form to the Milky Way, with its own spiral arms, central region, and vast population of stars. It lies relatively close in cosmic terms, making it one of the few galaxies that can be observed with the naked eye under dark skies. Observations show that the Milky Way and Andromeda are moving toward each other. This motion is not random, but the result of their mutual gravitational attraction. Over time, gravity is pulling these two large galaxies closer together, setting the stage for a future interaction. In about 4 billion years, the Milky Way and Andromeda are expected to collide. This event may sound dramatic, but it will not be a sudden crash, like objects colliding on Earth. Instead, it will be a slow and gradual process that unfolds over hundreds of millions of years. Stars within galaxies are separated by enormous distances, so direct collisions between individual stars are extremely unlikely. Instead, the galaxies will begin to pass through one another, their shapes becoming distorted as gravity reshapes their shape. As this process continues, long streams of stars will be pulled outward, forming extended arcs that stretch across space. Gas clouds within the galaxies may collide and compress, triggering bursts of new star formation. The overall appearance of both galaxies will change as they interact. Over time, the repeated passes between the Milky Way and Andromeda will cause them to merge into a single, larger galaxy. The spiral arrangements that define them today may be disrupted, and the final system could take on a more rounded or elliptical shape. This future merger is a natural part of how galaxies evolve. Large galaxies grow over time by merging with smaller ones, gradually increasing in size and complexity. The Milky Way itself has already experienced such mergers in the past. Evidence of these past interactions can still be seen today. Some stars within the Milky Way move in patterns that suggest they originated in other galaxies. These stars were once part of smaller systems that were absorbed, becoming part of the larger galaxy. The Milky Way is also surrounded by smaller satellite galaxies that continue to orbit it. These galaxies are slowly influenced by its gravity, and over time, some of them may be drawn in and absorbed as well. This ongoing process contributes to the growth of the galaxy. The interaction between galaxies does more than change their shape. It also redistributes gas, dust, and stars, creating new opportunities for star formation and altering the internal design of the system. Seen another way, collisions and mergers are not destructive events, but transformative ones. This is important because it shows that the Milky Way is not a fixed form. It is part of a larger network of galaxies, constantly interacting and changing over time. Its current form is only one stage in a much longer history of growth and evolution. Looking ahead, the future collision with Andromeda represents another step in that process. Although it will occur far beyond any human timescale, it highlights the dynamic nature of the universe and the ongoing movement of galaxies through space. Even now, the Milky Way continues to move within the local group, shaped by the gravitational pull of its neighbors. The quiet motion we cannot feel is part of a much larger pattern, one that connects our galaxy to others across the vastness of space. And as these slow movements continue, the Milky Way carries with it the history of past interactions, while moving steadily toward the changes that lie ahead. Seen this way, the future meeting with Andromeda is not an isolated event, but part of a larger pattern that has always shaped galaxies. The Milky Way has grown by interaction before, and it will continue to do so again. What changes is the scale. A merger with Andromeda would be one of the most dramatic events in the history of our galaxy, yet it would still follow the same underlying rules of gravity, motion, and gradual transformation. Galaxies are built through time by these encounters. Their shapes, their star populations, and their outer halos all carry the marks of earlier meetings. When we imagine the Milky Way billions of years from now, we are really imagining the next chapter in a process that began long before the Sun was born. The Milky Way is not made up of stars alone. Between the stars exists a vast and active environment filled with gas and dust, forming the raw material from which new stars are created. This material drifts through the galaxy in enormous clouds, shaping the life cycle of the Milky Way in a quiet but continuous process. These clouds are not evenly spread. In some regions, gas and dust gather into dense concentrations known as nebulae. Within these nebulae, conditions begin to change as gravity slowly pulls material inward. Over time, this inward pull causes the cloud to collapse, becoming denser and hotter at its center. As the material compresses, temperature and pressure increase. Eventually, the core of the collapsing cloud becomes hot enough for nuclear reactions to begin. At that moment, a new star is born. This process can take millions of years, unfolding gradually as gravity shapes the material into a stable and shining object. One of the most well-known examples of this process can be seen in the Orion Nebula. This region contains many young stars forming within a vast cloud of gas and dust. It offers a clear view of how stars begin their lives, providing insight into the early stages of stellar development. Not all stars are the same. Some form with large amounts of mass, becoming hot and bright stars that burn through their energy quickly. Others form with much less mass, becoming smaller stars that burn slowly and can last for billions of years. This difference in size affects how stars live and how they eventually reach the end of their life cycles. The Milky Way contains billions of planets orbiting around its stars. These planets form from the remaining material left over after a star is created. As gas and dust settle into a rotating disk around a young star, particles begin to stick together, gradually forming larger bodies over time. In some cases, these planets form within regions known as habitable zones. These are areas where conditions may allow liquid water to exist, creating the possibility for life to develop. While it is not yet known how common life is in the galaxy, the presence of so many planets suggests that the potential exists in many places. The spiral arms of the Milky Way are especially active regions for star formation. As gas clouds move through these arms, they encounter areas of higher density that compress the material. This compression increases the likelihood of collapse, triggering the formation of new stars. This ongoing process ensures that the galaxy remains active. While some stars are reaching the end of their lives, others are just beginning. The Milky Way is constantly renewing itself, with new stars appearing as older ones fade away. The gas and dust within the galaxy are also influenced by events such as supernova explosions. When massive stars reach the end of their lives and explode, they send material outward into space. This material mixes with existing gas and dust, enriching it with heavier elements. These elements are important because they allow for the formation of more complex shapes. Without them, planets like Earth would not exist. The cycle of star birth and death gradually increases the complexity of the galaxy over time. Even after stars form, the surrounding material continues to evolve. Some of it may be blown away by radiation from young stars, while other parts may remain and contribute to future generations of star formation. This creates a continuous cycle of change within the galaxy. This process matters because it is the foundation of everything we see in the Milky Way. Every star, every planet, and every element heavier than hydrogen and helium is part of this ongoing cycle. It is the mechanism through which the galaxy builds and rebuilds itself over time. From there, this cycle continues across the spiral arms and throughout the disk of the galaxy. Gas moves, clouds form, stars are born, and the process repeats. It is slow, steady, and constant, shaping the Milky Way in ways that continue to unfold. And within this vast cycle, our own sun was formed, along with the planets that orbit it, making us part of a much larger and ongoing story. Star formation also gives the Milky Way its changing appearance. The youngest stars are often bright and hot, illuminating the clouds around them and marking out active regions within the spiral arms. Older stars settle into the broader background of the galaxy, carrying with them the record of earlier episodes of formation. As a result, the Milky Way is never made of one generation of stars alone. It holds newborn stars, mature stars, and the remains of dead ones, all at the same time. The gas and dust drifting between them are both the leftovers of earlier lives and the material for future ones. This ongoing exchange makes the galaxy feel less like a static object and more like a living environment, one in which change is constant, even when it unfolds slowly. The Milky Way is not a random scattering of stars, but a highly organized system with distinct regions that each play a role in how the galaxy functions. Its arrangement has developed over billions of years, shaped by gravity, motion, and the gradual accumulation of matter. Understanding this design reveals how the galaxy maintains its form while remaining in constant motion. The most prominent part of the Milky Way is its disk. This is the flattened region where most of the galaxy's stars, gas, and dust are located. The disk stretches across the full width of the galaxy and is about 1,000 light-years thick, making it relatively thin compared to its overall size. Within this disk, stars orbit the center in broadly circular paths, creating a smooth and coordinated pattern of motion. Embedded within the disk are the spiral arms, where stars and gas are more densely concentrated. These regions are not fixed in place, but represent areas where material gathers as it moves through the galaxy. The disk itself is an active environment, constantly shaped by the movement of stars and the formation of new ones. At the center of the Milky Way lies the bulge, a dense and rounded region filled primarily with older stars. These stars tend to be redder and cooler, having existed for much longer than those found in the spiral arms. The bulge contains a large concentration of mass, including the central black hole, and plays a key role in the gravitational balance of the galaxy. The motion of stars in the bulge is less orderly than in the disk. Instead of following nearly circular paths, many stars move in more complex orbits, reflecting the dense and dynamic nature of this region. This creates a contrast between the relatively smooth motion of the disk and the more varied movement within the bulge. Surrounding both the disk and the bulge is a vast region known as the halo. The halo extends far beyond the visible boundaries of the galaxy and contains a sparse distribution of stars and clusters. Unlike the disk, the halo is roughly spherical in shape, enveloping the galaxy in all directions. The stars within the halo follow highly varied paths. Some move in elongated orbits that carry them far above and below the plane of the galaxy. These motions reflect the history of the Milky Way, including past interactions and mergers with smaller galaxies. Within the halo are globular clusters, which are dense groups of ancient stars that orbit the galaxy. These clusters are among the oldest forms in the Milky Way, providing valuable insight into its early formation. Their presence in the halo highlights the layered nature of the galaxy, with different components reflecting different stages of its history. A large portion of the Milky Way's mass is made up of dark matter, which forms an invisible framework surrounding the galaxy. Although it cannot be seen directly, Its gravitational influence is essential for holding the galaxy together. Without it, the observed motion of stars, especially in the outer regions, would not be possible. This dark matter extends well beyond the visible parts of the galaxy, forming a much larger shape that supports the disk and halo. It acts as a kind of hidden foundation, shaping the movement of stars and influencing the overall stability of the system. The arrangement of the Milky Way is not perfectly uniform. The disk is slightly warped at its outer edges, and some stars move above and below the main plane. These variations are likely caused by gravitational interactions with nearby galaxies and the uneven distribution of mass within the galaxy itself. Despite these irregularities, the overall design remains stable. The balance between gravity and motion allows the Milky Way to maintain its shape over long periods of time, even as its individual components continue to move and change. This form matters because it determines how the galaxy evolves. The distribution of stars, gas, and dark matter influences where new stars form, how material moves, and how the galaxy responds to external forces. What follows is that this shape continues to adapt. As stars are born and die, as gas flows through the disk, and as the galaxy interacts with its surroundings, the Milky Way slowly changes while preserving its overall form. In this sense, the galaxy is both stable and dynamic. Its arrangement provides a framework that endures, while its internal processes ensure that it is always evolving. Thinking about the Milky Way in terms of design also helps explain why different regions feel so different in character. The disk is rich in gas and young stars, the bulge is older and denser, and the halo is broad, faint, and ancient. Each part tells a different part of the galaxy's story. Together, they show that the Milky Way is layered, with its present form shaped by many earlier stages of growth. This layered design is one reason the galaxy can seem simple from a distance and deeply complicated when examined closely. A single band of light in the sky is, in reality, the visible expression of several overlapping systems, each with its own motion, history, and contribution to the whole. The Milky Way is not still. It is a vast rotating system, with all of its stars, gas, and dust moving together under the influence of gravity. This motion is steady and continuous, shaping the form of the galaxy while remaining almost impossible to sense from within it. Every star in the Milky Way orbits the galactic center. These orbits are not random, but follow patterns determined by the distribution of mass throughout the galaxy. Stars closer to the center tend to move more quickly, while those farther out follow wider paths, yet the overall system remains bound together. Our solar system is part of this motion. It travels around the center of the galaxy at a speed of about 514,000 miles per hour. This speed is far beyond anything experienced in daily life, yet it does not feel fast because everything around us is moving in the same direction at nearly the same rate. This shared motion creates a sense of stillness. There is no wind, no resistance, and no change in direction that would make the movement noticeable. Instead, the motion is smooth and constant, carrying the sun and its planets through the galaxy without interruption. It takes about 225 million years for the solar system to complete one full orbit around the Milky Way. This period is sometimes referred to as a cosmic year. Compared to the length of a human life, or even the entire span of human history, this is an almost unimaginable duration. Since the Sun formed about 4.6 billion years ago, it has completed only a small number of these galactic orbits. During that time, it has moved through different regions of the galaxy, encountering varying conditions as it travels along its path. The rotation of the Milky Way revealed something unexpected when scientists began to measure it more carefully. Based on the visible mass of the galaxy, stars farther from the center should move more slowly than those closer in. However, observations showed that stars in the outer regions were moving faster than expected. This difference could not be explained by the visible matter alone. The stars should have drifted away from the galaxy if only the observed mass were present. Instead, they remained in stable orbits, suggesting that there was additional mass that could not be seen. This led to the concept of dark matter. Although it does not emit or reflect light, dark matter exerts gravitational influence. It makes up most of the Milky Way's total mass and plays a critical role in holding the galaxy together. The presence of dark matter helps explain why the rotation of the galaxy behaves the way it does. It provides the additional gravitational pull needed to keep stars moving at the speeds that are observed, especially in the outer regions. The rotation of the galaxy is not perfectly uniform. The inner regions, including the central bar and bulge, rotate differently from the outer disk. This variation creates subtle shifts in the shape of the galaxy over time, contributing to the formation and maintenance of spiral patterns. As stars move through the galaxy, they do not remain fixed within the spiral arms. Instead, they pass in and out of these regions as they orbit the center. The arms themselves are patterns of density, not permanent groupings of the same stars. This continuous motion means that the Milky Way is always changing, even though its overall shape appears stable. Stars move along their paths, gas flows through the disk, and the arrangement of the galaxy slowly evolves. The balance between motion and gravity is what allows this system to remain intact. Stars move fast enough to avoid falling directly toward the center, but not so fast that they escape into space. This delicate balance maintains the galaxy as a coherent whole. Over long periods of time, this motion influences many aspects of the galaxy. It affects where stars form, how gas is distributed, and how the galaxy responds to interactions with other galaxies. It is a fundamental part of how the Milky Way functions. Even though we cannot feel this motion, it is always present. Every moment, the Sun carries us through space as part of its orbit around the galaxy. The stars around us are doing the same, each following its own path within the larger system. Seen another way, the Milky Way is not just a design, but a process in motion. Its rotation is a constant, shaping its past, guiding its present, and influencing its future as it continues to turn through the vastness of space. Rotation is therefore not just one feature among many. It is one of the main reasons the Milky Way has the form we recognize at all. The flattened disk, the repeated passage through spiral arms, and the large-scale organization of stars all depend on this continuous turning. Motion shapes form, and shape guides later motion in return. That is why the galaxy can remain coherent over such long spans of time. Nothing is fixed, yet nothing is entirely loose. Everything is part of a sustained balance that keeps the Milky Way together while still allowing it to change. The more we understand this balance, the easier it becomes to see the galaxy not as a frozen object in space, but as an organized movement unfolding across hundreds of millions of years. The spiral arms of the Milky Way are among its most recognizable features, forming sweeping patterns that extend outward from the central region. These arms give the galaxy its distinctive shape, but they are not fixed arrangements made of the same stars. Instead, they are regions where stars and gas are more densely concentrated, shaped by the motion and gravity within the galaxy. As the Milky Way rotates, material does not remain locked within a single arm. Stars, gas, and dust move through the arms over time, entering and leaving these regions as they orbit the center. The arms themselves are better understood as patterns of density, created by waves that move through the disk of the galaxy. These density waves act like areas of compression. As gas clouds travel through them, they are squeezed together, increasing their density. This process makes it more likely for gravity to take over, leading to the collapse of the cloud and the formation of new stars. As a result, the spiral arms are closely linked to star formation. Because of this ongoing activity, the spiral arms often contain many young, bright stars. These stars shine intensely, making the arms stand out more clearly compared to other parts of the galaxy. Over time, as stars move away from the regions where they formed, they become part of the broader distribution of stars within the disk. Our solar system is located within a smaller feature known as the Orion Arm. This is not one of the major spiral arms, but a minor arm positioned between two larger ones. It is a relatively calm region with lower densities of stars compared to the more active inner areas of the galaxy. This location has important consequences. In regions closer to the center, stars are packed more closely together, and energetic events such as supernova explosions occur more frequently. These events can release intense radiation, which could have significant effects on nearby planetary systems. In contrast, the region where our solar system is located experiences fewer of these extreme events. The greater distance between stars provides a more stable environment, where conditions remain relatively steady over long periods of time. This stability may have played a role in allowing life to develop and persist on Earth. When we look at the Milky Way from Earth, we see it as a soft band of light stretching across the sky. This appearance is the result of looking along the plane of the galaxy, where the concentration of stars is greatest. The light from countless distant stars blends together, creating a continuous glow. The brightest and most densely populated regions of this band lie in the direction of the galactic center. In that direction, the number of stars increases significantly, creating a richer and more complex appearance. In other directions, where there are fewer stars, the band becomes fainter. Interstellar dust also plays a role in shaping what we see. Dust clouds within the galaxy block light from more distant stars, creating dark lanes that cut across the brighter regions. These features give the Milky Way its textured appearance, with both bright and shadowed areas visible under dark skies. The spiral design of the galaxy is maintained over time by the ongoing movement of stars and gas. Although individual stars move in and out of the arms, the overall pattern remains, sustained by the underlying dynamics of the galaxy. As the Milky Way continues to rotate, the spiral arms shift gradually. New stars form within them, while older stars move away, contributing to the changing distribution of material within the disk. This process ensures that the galaxy remains active and evolving. The position of our solar system within the Orion Arm means that we are part of this larger form, even if we cannot see it from the outside. We experience the galaxy from within, observing only a small part of its full extent. Despite this limited view, careful observation and measurement have allowed scientists to map the shape of the Milky Way. By studying the motion of stars and the distribution of gas, they have been able to infer the shape and arrangement of its spiral arms. That matters because it helps us understand our place within the galaxy. We are not located at the center, nor are we in one of the most extreme regions. Instead, we occupy a position that is relatively quiet, yet still connected to the larger arrangement. Next, as the galaxy continues its slow rotation, stars will keep moving through the spiral arms, and new stars will continue to form. The pattern will remain, even as its individual components change over time. In this sense, the spiral arms represent both stability and motion, a lasting design shaped by processes that are constantly unfolding. Our position within a smaller arm also affects the way we build our picture of the galaxy. Because we cannot step outside the Milky Way and look back at it directly, much of our knowledge comes from tracing the distribution of stars, gas, and dust from inside the system itself. Astronomers measure distances, motions, and patterns of light, then use those clues to reconstruct the larger form. This makes the study of our own galaxy unusually challenging, yet also unusually intimate. We are investigating the place we inhabit while being unable to leave it for a wider view. In a strange way, the Orion Arm is both our address and our observation point, the quiet corner from which we try to understand the full sweep of the spiral around us. The Milky Way appears in the night sky as a soft and luminous band of light, stretching from one horizon to the other. This faint glow has been observed by people throughout history, long before its true nature was understood. It looks like a pale river of light flowing across the darkness, made up of countless distant stars that are too faint to be seen individually. This appearance is the result of our position within the galaxy. We are located inside the disk of the Milky Way, and when we look outward along this disk, we are looking through a dense concentration of stars. The light from these stars blends together, creating the continuous band that we see in the sky. The name Milky Way comes from this visual effect. Early observers described it as resembling spilled milk across the sky, and this image has remained part of its identity ever since. The ancient Greeks referred to it as galaxias, meaning milky circle, and from this word the term galaxy was later derived. In places far from artificial light, the Milky Way becomes much more visible. Thousands of individual stars can be seen, along with brighter clusters and darker regions that add texture to the band. The contrast between light and dark gives the Milky Way its layered appearance, making it one of the most striking features of the night sky. The brightness of the Milky Way is not uniform. In the direction of the galactic center, the band appears brighter and more densely packed with stars. In other directions, where there are fewer stars, it becomes fainter and more diffuse. This variation reflects the form of the galaxy and our position within it. Interstellar dust plays a significant role in shaping what we see. These tiny particles are spread throughout the galaxy and can block light from more distant stars. When this happens, it creates dark lanes that cut across the brighter regions of the Milky Way, adding depth and contrast to its appearance. These dark regions are not empty spaces, but areas where dust is concentrated enough to obscure the light behind it. Beyond these clouds, many more stars exist, but their light cannot reach us directly. This means that what we see is only part of the full picture of the galaxy. The Milky Way's appearance also changes, depending on the time of year and the observer's location on Earth. As the Earth orbits the Sun, different parts of the galaxy come into view during the night. This creates a shifting perspective, allowing different regions of the Milky Way to be observed at different times. From some locations, especially in the southern hemisphere, the central region of the galaxy is more clearly visible. In these areas, the Milky Way appears brighter and more detailed, revealing a richer view of its shape. From other locations, the view is more limited, but still provides a sense of its vastness. Even though the Milky Way appears as a continuous band, it is made up of individual stars spread across enormous distances. Some of these stars are relatively close, while others are so distant that their light has traveled for thousands of years before reaching Earth. This means that when we look at the Milky Way, we are also looking back in time. The light we see represents different moments in the past, depending on how far away each star is. Seen another way, the night sky becomes a record of the galaxy's history, preserved in light. The Milky Way is only one of many galaxies in the universe, yet it is the only one we can see from the inside. This gives it a unique appearance, different from the distant galaxies observed through telescopes. Instead of seeing its full shape, we experience it as a band of light that surrounds us. This perspective makes it more difficult to understand the true arrangement of the galaxy, but it also creates a sense of immersion. We are not looking at the Milky Way from the outside, but living within it, surrounded by its stars. As observation techniques have improved, scientists have been able to move beyond what the human eye can see. By using different forms of light, such as infrared and radio waves, they have revealed designs hidden behind dust and mapped the galaxy in greater detail. What appears to us as a simple glowing band is in reality a vast and complex system. It contains regions of intense activity, areas of star formation, and forms that extend far beyond what is visible. Yet even with this knowledge, the visual experience of the Milky Way remains powerful. It is a reminder of the scale of the galaxy and our place within it, a quiet presence in the night sky that connects us to the larger universe. As a result, the Milky Way is both something we can observe and something we are part of, a shape that surrounds us while stretching far beyond what we can fully see or understand. For all its complexity, the Milky Way still retains a simple emotional power when seen under a truly dark sky. The band of light overhead can feel quiet and distant, yet it is also a visible reminder that we belong to something far larger than everyday life suggests. What looks at first like a faint haze turns out to be the combined light of unimaginable numbers of stars, arranged within an arrangement with depth, history, and motion. That realization is part of what makes the Milky Way worth lingering over. It invites patience. The longer we consider it, the more the familiar night sky opens into a place of scale and meaning, one that continues far beyond the limits of ordinary sight. When we look at the Milky Way with our eyes alone, we are only seeing a small part of what is truly there. The visible light that reaches us shows stars and some glowing regions of gas, but much of the galaxy remains hidden behind clouds of dust. These dust clouds block shorter wavelengths of light, preventing us from seeing deeper into the structure of the galaxy. This limitation means that for a long time, the true form of the Milky Way was difficult to understand. The central regions, in particular, were obscured, making it impossible to see directly into the most crowded and active parts of the galaxy using visible light alone. What appeared as dark gaps in the sky were not empty spaces, but areas where dust prevented light from passing through. To overcome this, scientists began observing the galaxy using other forms of light. Different wavelengths can pass through dust more effectively, revealing structures that are otherwise hidden. Infrared light, for example, can penetrate dust clouds and provide a clearer view of regions closer to the galactic center. Infrared observations have revealed a much richer and more detailed picture of the Milky Way. Where visible light shows dark lanes, infrared light often reveals dense clusters of stars and active regions filled with energy. This has allowed astronomers to study areas that were once completely concealed. Radio waves provide another way to explore the galaxy. These waves can travel through dust without being blocked, making them especially useful for mapping the distribution of gas within the Milky Way. By observing radio emissions, scientists can trace the movement of hydrogen gas, which is one of the main components of the galaxy. This has made it possible to map the spiral arms of the Milky Way more accurately. Even though we cannot step outside the galaxy to view its full shape, these measurements allow scientists to reconstruct its structure based on the movement and distribution of material. X-ray observations reveal yet another layer of the galaxy. These high-energy wavelengths highlight extreme environments, such as regions around black holes, neutron stars, and supernova remnants. These are places where energy is released in powerful bursts, creating conditions very different from the calmer regions where stars like our Sun are found. By combining information from visible light, infrared, radio waves, and X-rays, scientists can build a more complete understanding of the Milky Way. Each type of light reveals a different aspect of the galaxy, adding to a layered picture that would not be possible from any single method alone. This approach shows that the Milky Way is far more complex than it first appears. What looks like a simple band of light is actually a combination of many overlapping systems, each visible in different ways depending on how it is observed. The ability to see beyond visible light has also changed how we study star formation. Many of the regions where stars are being born are hidden within dense clouds of gas and dust. Infrared observations allow scientists to look inside these clouds and observe the early stages of star formation. This has provided insight into how stars begin their lives, how they gather mass, and how they interact with their surroundings. It has also revealed that star formation is happening in many parts of the galaxy at the same time, rather than being confined to a few isolated regions. Looking at the Milky Way across different wavelengths also helps scientists understand how energy moves through the galaxy. Radiation, particles, and magnetic fields all play a role in shaping the environment between stars. These processes are not always visible in ordinary light, but become clear when viewed through other forms of observation. This matters because it expands our understanding of what the galaxy really is. It is not just a collection of stars that can be seen with the eye, but a complex system with layers that extend beyond visible light. Each layer adds depth to our understanding, revealing processes that are otherwise hidden. What happens next is that as technology continues to improve, observations become more detailed and more precise. New instruments allow scientists to detect fainter signals and explore regions that were previously out of reach. In this way, the Milky Way becomes more than something we look at. It becomes something we investigate from multiple perspectives, each one revealing a different part of the whole. Even though we remain inside the galaxy, unable to step outside and see it directly, these methods allow us to build a picture of its structure and behavior. Piece by piece, the hidden parts of the Milky Way are brought into view, and as more of these hidden layers are revealed, the galaxy becomes not just a distant object, but a deeply understood system, one that continues to unfold as our ability to observe it improves. Not all regions of the Milky Way are calm and steady. Alongside the quiet movement of stars and the slow formation of new ones, there are also extreme events that release enormous amounts of energy. These events mark the final stages of stellar life and play a crucial role in shaping the galaxy. Stars do not last forever. Each one is powered by nuclear reactions at its core, where lighter elements are fused into heavier ones, releasing energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. As long as this balance is maintained, the star remains stable. Over time, however, the fuel within a star begins to run out. The exact way a star evolves depends on its mass. Smaller stars, like our Sun, change slowly and gently, expanding into larger forms before shedding their outer layers. Larger stars follow a much more dramatic path. Massive stars burn through their fuel quickly, reaching the end of their lives in a relatively short time. When they can no longer sustain the balance between pressure and gravity, their cores collapse. This collapse happens rapidly, triggering a powerful explosion known as a supernova. A supernova releases an immense amount of energy in a brief moment. For a short time, the exploding star can outshine entire regions of the galaxy. The outer layers of the star are thrown outward into space, carrying with them the elements that were formed during the star's lifetime. These explosions are not just destructive events, they are also creative ones. The heavier elements produced inside stars, such as iron and other complex atoms, are spread into the surrounding gas and dust. This enriched material becomes part of future generations of stars and planets. In some cases, the core that remains after a supernova becomes a neutron star. This is an extremely dense object, where matter has been compressed to such an extent that a small amount contains an enormous mass. Neutron stars can spin rapidly, emitting beams of radiation that sweep through space. When these beams are aligned with Earth, they can be detected as regular pulses of energy. These objects are known as pulsars. Their steady signals allow scientists to study extreme physical conditions that cannot be reproduced on Earth. In other cases, if the original star was massive enough, the collapse continues even further, forming a black hole. These objects have gravity so strong that nothing can escape once it passes a certain boundary. Black holes can be found throughout the Milky Way, formed from the remnants of massive stars. The presence of these extreme objects shows that the galaxy contains a wide range of environments. Some regions are quiet and stable, while others are shaped by powerful and sometimes violent events. Together, they form a complete picture of the galaxy's life cycle. Supernova remnants can remain visible for long periods after the explosion. Expanding clouds of gas continue to move outward, interacting with the surrounding environment. These remnants can trigger new star formation by compressing nearby gas clouds. This creates a connection between the end of one star and the beginning of others. The material released in a supernova becomes the foundation for future stars, continuing the cycle of formation and change within the galaxy. The elements produced in these processes are essential for the existence of planets and life. Without the repeated cycle of stellar birth and death, the universe would remain simple, composed mainly of hydrogen and helium. The complexity we observe today is the result of these ongoing transformations. This matters because it connects the largest scales of the galaxy to the smallest details of our own existence. The atoms that make up our bodies were formed inside stars that lived and died long before the sun was created. When we look at the Milky Way, we are not only seeing distant stars, but also the results of countless cycles of creation and destruction. Each generation of stars builds upon the last, gradually increasing the complexity of the galaxy. What happens next is that this cycle continues. New stars form from enriched material, live their lives, and eventually return that material to the galaxy. The process does not stop, but repeats across vast stretches of time. In this way, the Milky Way is constantly renewing itself. Even as individual stars reach the end of their lives, the galaxy as a whole continues to evolve, shaped by the balance between stability and change. This balance gives the galaxy its character. It is neither entirely calm nor entirely violent, but a system where both extremes exist together, each contributing to the ongoing story of the Milky Way. Within the Milky Way, stars are not always spread out evenly. In many regions, they are gathered together in groups known as star clusters. These clusters are important because they provide insight into how stars form, evolve, and relate to one another within the larger structure of the galaxy. There are two main types of star clusters found in the Milky Way. The first are open clusters, which are relatively young and loosely bound groups of stars. These clusters are usually found within the disk of the galaxy, often located along the spiral arms where star formation is most active. Open clusters form from the same cloud of gas and dust, meaning that all the stars within them are born at roughly the same time. Because of this shared origin, they often have similar chemical compositions and ages. This makes them useful for studying how stars develop over time under similar conditions. The stars within open clusters are not tightly held together. Over time, gravitational interactions with other stars and the movement of the galaxy gradually pull these clusters apart. As a result, open clusters tend to disperse over millions or hundreds of millions of years, their stars becoming part of the general population within the galaxy. The second type of cluster is known as a globular cluster. These are very different from open clusters in both structure and age. Globular clusters are tightly bound, spherical groups of stars that can contain hundreds of thousands or even millions of stars packed into a relatively small region. These clusters are among the oldest objects in the Milky Way. Many of them formed early in the galaxy's history, making them valuable records of its past. The stars within globular clusters are typically older, cooler, and less rich in heavy elements compared to younger stars found in the disk. Globular clusters are not located within the main disk of the galaxy. Instead, they are found in the halo, orbiting the Milky Way in extended paths that take them far above and below the galactic plane. Their distribution provides clues about the early formation of the galaxy and the processes that shaped it. Because globular clusters are so densely packed, the stars within them interact more frequently than those in less crowded regions. These interactions can influence the motion of stars within the cluster and lead to complex gravitational effects that are studied in detail by astronomers. The contrast between open clusters and globular clusters highlights the diversity within the Milky Way. Open clusters represent recent star formation, while globular clusters preserve the conditions of the early galaxy. Together, they show how the galaxy has changed over time. Studying star clusters also helps scientists understand stellar evolution. Because the stars in a cluster form at the same time, differences in their appearance can be linked to differences in mass rather than age. This makes clusters valuable natural laboratories for testing theories about how stars live and change. Clusters can also reveal information about the distribution of matter in the galaxy. By observing their motion and position, scientists can gain insight into the gravitational forces acting within the Milky Way, including the influence of dark matter. Some clusters contain stars that are beginning to leave the group, forming streams that stretch out into space. These stellar streams can trace the past motion of clusters and provide further evidence of how the galaxy has evolved through time. Over long periods, the gradual dispersal of open clusters contributes to the overall population of stars within the disk. The stars that once formed together become indistinguishable from others, blending into the larger structure of the galaxy. Globular clusters, on the other hand, remain bound for much longer. Their strong gravitational attraction allows them to persist for billions of years, maintaining their structure even as they orbit the galaxy. This matters because star clusters provide a link between individual stars and the larger galaxy. They show how stars are born together, how they evolve, and how they eventually become part of the broader system. What happens next is that clusters continue to form, evolve, and disperse. New open clusters appear in regions of active star formation, while older ones fade into the background of the galaxy. At the same time, globular clusters continue their long orbits through the halo, preserving a record of the early Milky Way. Their presence reminds us that the galaxy contains not only the results of recent activity, but also the remnants of its distant past. In this way, star clusters help bridge the gap between the small-scale processes of individual stars and the large-scale structure of the galaxy, showing how both are connected through time. Between the stars of the Milky Way lies a vast and often overlooked environment known as the interstellar medium. Although it may appear empty at first glance, this space is filled with gas, dust, and energetic particles that play a crucial role in the life of the galaxy. It is within this medium that stars are born, evolve, and return material back into the galaxy. The interstellar medium is made up primarily of hydrogen, along with smaller amounts of helium and trace elements formed in earlier generations of stars. This material exists in different states, ranging from cold and dense clouds to hot and diffuse regions. These variations create a complex and dynamic environment that changes over time. In its coldest form, the interstellar medium gathers into molecular clouds. These are dense regions where gas particles come together and begin to interact more closely. Within these clouds, temperatures are low enough for molecules to form, creating the conditions needed for star formation to begin. As gravity pulls material within these clouds together, certain regions become denser and more concentrated. Over time, these regions may collapse further, eventually giving rise to new stars. In this way, the interstellar medium acts as the starting point for the formation of stellar systems. Not all parts of the interstellar medium are cold and dense. Some regions are heated by nearby stars or by energetic events such as supernova explosions. These hotter regions contain ionized gas, where atoms have lost electrons due to high-energy conditions. This creates glowing clouds that can be observed across the galaxy. The movement of gas within the interstellar medium is not random. It is influenced by gravity, radiation, and the motion of stars. As stars move through the galaxy, they interact with the surrounding medium, shaping its structure and contributing to its ongoing evolution. Supernova explosions play a particularly important role in this process. When a massive star explodes, it sends shockwaves through the interstellar medium, compressing gas and triggering new regions of star formation. At the same time, these explosions enrich the medium with heavier elements. This continuous exchange of material ensures that the interstellar medium is never static. It is constantly being shaped by the life cycles of stars, with matter flowing between different phases and regions. Gas becomes stars, stars release material, and that material becomes part of new stars. Magnetic fields also influence the behavior of the interstellar medium. Although they are invisible, these fields affect the motion of charged particles and can guide the flow of gas across large distances. They add another layer of complexity to the environment between the stars. Cosmic rays, which are high-energy particles traveling through space, move through the interstellar medium as well. These particles interact with gas and dust, contributing to the energy balance within the galaxy. They are another example of how even seemingly empty space is filled with activity. Dust within the interstellar medium plays a subtle but important role. These tiny particles can absorb and scatter light, affecting how we observe the galaxy. They also provide surfaces on which molecules can form, helping to build more complex chemical structures. The interstellar medium connects all parts of the Milky Way. It links regions of star formation with areas where stars have ended their lives, creating a continuous cycle of matter and energy. Without this medium, the galaxy would not be able to sustain the processes that define it. This matters because the interstellar medium is the foundation of change within the galaxy. It is the source of new stars and the recipient of material from old ones. It carries the history of the galaxy while also shaping its future. What happens next is that this medium continues to shift and evolve. Gas flows through the spiral arms, clouds form and collapse, and the cycle of star formation continues across the galaxy. Even though it cannot be seen directly in most cases, the interstellar medium is always present. It fills the space between stars, quietly shaping the Milky Way through processes that unfold over immense periods of time. In this way, The space between stars is not empty, but full of activity and potential, forming an essential part of the galaxy's ongoing story. The Milky Way is surrounded by smaller galaxies that orbit it, forming part of its extended environment. These are known as satellite galaxies, and they play an important role in the ongoing growth and evolution of the Milky Way. Although they are much smaller than the main galaxy, their interactions leave lasting effects that can still be observed today. Among the most well-known of these are the Large Magellanic Cloud and the Small Magellanic Cloud. These are visible from the southern hemisphere as faint patches of light in the sky. They are irregular in shape, lacking the clear spiral pattern seen in larger galaxies, and are composed of stars, gas, and dust, similar to those found in the Milky Way. These satellite galaxies are bound to the Milky Way by gravity. As they move through space, they follow extended paths that bring them close to the larger galaxy over long periods of time. Their motion is slow and gradual, unfolding over millions and billions of years. As these smaller galaxies orbit the Milky Way, gravitational forces begin to stretch and distort them. This process can pull stars away from the satellite galaxies, creating long streams of stars that extend outward into space. These are known as stellar streams, and they act as visible traces of past interactions. Stellar streams can stretch across large distances, forming arcs that wrap around the Milky Way. By studying their shape and motion, scientists can learn about the gravitational structure of the galaxy, including the distribution of both visible matter and dark matter. These streams also provide evidence that the Milky Way has grown over time by absorbing smaller galaxies. Many of the stars now found in the galaxy may have originally formed elsewhere, later becoming part of the Milky Way through these gradual mergers. The process of merging does not happen all at once. Instead, it unfolds slowly as the smaller galaxy is gradually pulled apart. Over time, its stars become more widely distributed, blending into the larger galaxy while still preserving subtle patterns of motion. This ongoing interaction contributes to the growth of the Milky Way. Each absorbed galaxy adds its stars, gas, and dark matter to the larger system, increasing its mass and complexity. The galaxy we see today is the result of many such interactions over billions of years. The presence of satellite galaxies also affects the structure of the Milky Way. Their gravitational influence can create slight distortions in the disk, contributing to features such as warps and ripples that extend across the galaxy. Some satellite galaxies are still intact, continuing their orbits around the Milky Way. Others have already been partially or completely absorbed, leaving behind only the streams of stars that mark their former existence. These interactions are not unique to the Milky Way. Many galaxies grow in similar ways, gradually merging with smaller systems and incorporating them into their structure. This process is a fundamental part of how galaxies evolve. Studying satellite galaxies and stellar streams helps scientists understand the history of the Milky Way. By tracing the paths of these streams and analyzing their composition, it is possible to reconstruct past events that shaped the galaxy. This matters because it shows that the Milky Way is not a closed system. It is constantly interacting with its surroundings, exchanging material and responding to the gravitational influence of nearby objects. What happens next is that these interactions will continue. Satellite galaxies will keep orbiting, some will be drawn closer, and others may eventually be absorbed into the Milky Way. At the same time, new streams of stars may form as these processes unfold, adding further complexity to the structure of the galaxy. These features provide a record of the galaxy's past, while also pointing toward its future. Even though these changes occur over timescales far beyond human experience, they are happening now. The Milky Way continues to grow and evolve, shaped by the quiet but persistent influence of the galaxies around it. In this way, the satellite galaxies and their streams of stars are not separate from the Milky Way, but part of its extended system, contributing to its ongoing story and development. The central region of the Milky Way is one of the most energetic and complex environments in the entire galaxy. While much of this activity is hidden from direct view, it plays a critical role in shaping the behavior of the galaxy as a whole. This region is far more crowded than the outer areas, with stars packed closely together and moving at much higher speeds. At the heart of this region lies the supermassive black hole, Sagittarius A star. Although it cannot be seen directly, its influence extends across a large portion of the central area. The strong gravitational pull of this object affects the motion of nearby stars, drawing them into fast and tightly curved paths. Surrounding the central black hole is a dense concentration of stars, gas, and dust. These materials interact in ways that create bursts of energy, especially when gas is pulled inward and heated to extreme temperatures. As this gas accelerates, it can emit radiation across multiple wavelengths, including X-rays and infrared light. Because visible light is blocked by thick clouds of dust, much of the activity in this region can only be studied using specialized instruments. Infrared observations allow scientists to see through the dust, revealing clusters of stars and the movement of material near the center. X-ray observations highlight the most energetic events, where matter is heated to very high temperatures. The density of stars in this central region leads to frequent gravitational interactions. Stars can influence one another's paths more directly than in the outer regions of the galaxy. This creates a dynamic environment where motion is less orderly and more complex. In addition to stars, the central region contains large amounts of gas that continue to move inward. Some of this material may form new stars, while some may be drawn closer to the black hole. As gas approaches the black hole, it can form a rotating disk, heating up as it moves faster and faster. This process releases energy, contributing to the overall activity of the galactic center. Although the Milky Way is not currently as active as some other galaxies, there is still ongoing energy release that can be detected through careful observation. The central region also contains strong magnetic fields that influence the movement of charged particles. These fields can shape the flow of gas and contribute to the formation of structures that extend outward from the center. Evidence suggests that the Milky Way may have been more active in the past. Signs of previous energetic events, such as large-scale outflows of gas, indicate that the central black hole may have released more energy at earlier stages in the galaxy's history. These past events may have affected the distribution of gas within the galaxy, influencing where new stars formed. In this way, the activity at the center can have consequences that extend far beyond its immediate surroundings. The hidden nature of the galactic center adds to its complexity. Much of what happens there cannot be seen directly, but must be inferred through indirect observation. By studying the motion of stars and the behavior of gas, scientists are able to piece together a detailed understanding of this region. This matters because the central region acts as a kind of anchor for the galaxy. Its gravitational influence helps maintain the overall organization of the Milky Way, while its energetic processes contribute to the internal dynamics of the system. What happens next is that the central region will continue to evolve. Gas will keep flowing inward. Stars will continue to move through this crowded environment, and the black hole will remain a powerful influence at the heart of the galaxy. Even though we are far from this region, its effects are still felt across the Milky Way. It shapes the motion of stars, influences the distribution of matter, and plays a role in the long-term evolution of the galaxy. In this way, the galactic center is both hidden and essential, a region that cannot be seen directly with the eye, yet remains central to understanding how the Milky Way functions as a whole. Beyond the visible disk of the Milky Way lies a vast and much more diffuse region known as the outer halo. This area extends far beyond the bright band of stars that can be seen in the night sky, forming a wide and spherical envelope around the galaxy. Although it contains far fewer stars than the central regions, it is an essential part of the Milky Way's overall structure. The halo is not easily observed with the naked eye. Unlike the dense disk, where stars are closely packed, the halo contains stars that are spread out across immense distances. These stars are often older and less luminous, making them more difficult to detect without specialized instruments. Many of the stars found in the halo are among the oldest in the galaxy. They formed early in the Milky Way's history, before the disk had fully developed its present form. Because of this, they provide valuable information about the conditions that existed during the early stages of the galaxy's formation. The motion of stars in the halo differs from those in the disk. Instead of moving in relatively flat and circular paths, halo stars follow more varied and elongated orbits. Some travel far above and below the plane of the galaxy, tracing paths that reflect the complex gravitational history of the Milky Way. This difference in motion suggests that the halo has a different origin from the disk. Many of its stars are believed to have come from smaller galaxies that were absorbed into the Milky Way over time. As these galaxies merged, their stars were scattered into wide orbits, becoming part of the halo. The halo also contains globular clusters, which are tightly bound groups of very old stars. These clusters orbit the galaxy in extended paths and are found primarily in the halo rather than in the disk. Their presence adds to the evidence that the halo preserves some of the oldest components of the Milky Way. In addition to stars and clusters, the halo is dominated by dark matter. This invisible component extends far beyond the visible parts of the galaxy and makes up most of its total mass. Although it cannot be seen directly, its gravitational influence is essential for understanding how the galaxy behaves. The existence of dark matter in the halo helps explain why stars in the outer regions of the galaxy move at the speeds that they do. Without this additional mass, the outer parts of the Milky Way would not be able to remain gravitationally bound. The halo is not perfectly smooth or uniform. It contains streams of stars and other structures that reflect past interactions with smaller galaxies. These features provide a record of the Milky Way's history, showing how it has grown through mergers over billions of years. Some of these stellar streams stretch across large portions of the halo, forming faint arcs that can be traced through careful observation. By studying these streams, scientists can learn about the paths of past mergers and the distribution of mass within the galaxy. The outer halo extends much farther than the visible disk, reaching distances that are difficult to measure precisely. It represents the true outer boundary of the Milky Way, far beyond the regions that can be easily observed. Even though the halo contains relatively few stars compared to the disk, its total mass is significant due to the presence of dark matter. This makes it a critical component of the galaxy, influencing the motion of stars across all regions. The existence of the halo shows that the Milky Way is not limited to the bright areas we can see. It is a much larger system, with layers that extend far beyond the visible light that reaches us. This matters because it changes our understanding of the galaxy's scale. What appears as a defined structure in the night sky is actually only a small part of a much larger system that surrounds us. What happens next is that the halo continues to evolve as the Milky Way interacts with its surroundings. New stars may be added through future mergers, while existing structures gradually change over time. Even now, the halo carries the history of the galaxy within it. The motion of its stars, the presence of clusters, and the patterns of stellar streams all reflect events that took place long ago. In this way, the outer halo serves as both a boundary and a record. It marks the extent of the Milky Way while preserving the evidence of how it formed and grew. Although it is faint and difficult to observe, the halo is an essential part of the galaxy's identity. It completes the picture of the Milky Way as a system that extends far beyond what can be seen, shaped by processes that continue to unfold over immense periods of time. As we consider the full scale of the Milky Way, the halo reminds us that much of the galaxy exists beyond our immediate perception. It is a quiet and distant region, yet one that plays a fundamental role in holding the galaxy together and revealing its past. The Milky Way exists as a stable and coherent system because of the balance between mass and gravity. Every star, cloud of gas, and unseen component within the galaxy contributes to a complex gravitational network that holds everything together. Without this balance, the galaxy would not maintain its form, and its stars would drift apart into space. Mass is the key factor that determines how gravity operates within the galaxy. The greater the mass of an object, the stronger its gravitational pull. In the Milky Way, this mass is distributed across stars, gas, dust, and a large amount of dark matter that extends far beyond the visible regions. The total mass of the Milky Way is estimated to be more than 1 trillion times that of the Sun. This immense mass creates a gravitational field strong enough to bind the galaxy together, keeping stars in orbit around the center and maintaining the overall structure of the system. Gravity acts as the force that governs motion within the galaxy. Stars do not move randomly, but follow paths shaped by the distribution of mass. The closer a star is to a region of high mass, the stronger the gravitational influence it experiences. In the central regions, where mass is more concentrated, stars move more quickly. In the outer regions, where mass is more spread out, stars follow wider and slower paths. However, observations have shown that stars in the outer parts of the galaxy move faster than expected, indicating the presence of additional unseen mass. This unseen mass is known as dark matter, Although it cannot be observed directly, its gravitational effects are essential for explaining the motion of stars. Dark matter forms a large halo around the Milky Way, extending well beyond the visible disk. The presence of dark matter ensures that the galaxy remains bound together. Without it, the outer regions would not have enough gravitational pull to keep stars in orbit, and the galaxy would gradually disperse. The balance between gravity and motion is what allows the Milky Way to remain stable over long periods of time. Stars move fast enough to avoid collapsing inward toward the center, but not so fast that they escape the galaxy's gravitational pull. This delicate balance maintains the overall form of the galaxy. The distribution of mass within the galaxy also affects its shape. The concentration of mass in the disk leads to its flattened appearance, while the extended halo of dark matter gives the galaxy a much larger and more spherical outer region. In addition to holding the galaxy together, gravity influences how it changes over time. It drives the collapse of gas clouds, leading to the formation of new stars. It also governs interactions between stars and the movement of material within the galaxy. The Milky Way is not perfectly uniform. Variations in mass distribution create small distortions, such as the slight warp observed in the outer disk. These features are influenced by gravitational interactions with nearby galaxies and the uneven distribution of matter. Despite these variations, the overall balance remains stable. The forces at work are finely tuned, allowing the galaxy to evolve slowly without losing its coherence. This matters because it shows that the Milky Way is not simply a collection of objects, but a system governed by physical laws that operate on a vast scale. The interplay between mass and gravity shapes everything within the galaxy, from the motion of stars to the formation of new structures. What happens next is that this balance continues to guide the evolution of the galaxy. As stars form and die, as gas moves through the disk, and as the galaxy interacts with its surroundings, the distribution of mass changes gradually. These changes in turn influence the gravitational field, creating a continuous cycle of adjustment. The galaxy responds to these shifts while maintaining its overall stability. Even though these processes occur over immense periods of time, they are always active. The Milky Way is constantly balancing the forces that shape it, preserving its form while allowing for gradual change. In this way, gravity acts as both a stabilizing force and a driver of evolution. It holds the galaxy together, while also guiding the processes that allow it to grow and transform. As we consider the Milky Way as a whole, it becomes clear that its stability is not the result of stillness, but of continuous motion balanced by gravity. This balance allows the galaxy to exist as a long-lasting system, one that has endured for billions of years and will continue far into the future. The Milky Way is vast, but it is only one of many galaxies that fill the universe. Beyond its outer halo, there are countless other systems, each with their own stars, gas, and history. When viewed in this wider context, the Milky Way becomes part of a much larger pattern, one that extends across unimaginable distances. Galaxies are not spread evenly through space. Instead, they are arranged in groups and clusters, connected by gravity and shaped by the expansion of the universe. The Milky Way belongs to a small collection known as the local group. which includes several dozen galaxies bound together over long periods of time. Beyond the local group lie larger clusters, containing hundreds or even thousands of galaxies. These clusters are connected by vast filaments of matter, forming a web-like pattern across the universe. Between these filaments are enormous regions with very few galaxies, creating a structure that is both ordered and expansive. This large-scale arrangement is often described as the cosmic web. It is made up of matter distributed across immense distances, shaped by gravity, acting over billions of years. The Milky Way is one small part of this structure, located within a region where galaxies have gathered together. Each galaxy within this web has its own history, shaped by the same fundamental processes. Gas collapses under gravity, stars form, galaxies merge, and structures evolve over time. The Milky Way follows this same pattern, reflecting the broader behavior of the universe. When we observe distant galaxies, we are also looking back in time. Because light takes time to travel, the light from faraway galaxies shows them as they were millions or even billions of years ago. This allows scientists to study how galaxies change over time. By comparing these observations, it becomes clear that galaxies have evolved significantly. Early in the universe, galaxies were smaller and less organized. Over time, they merged and grew, forming the larger and more structured systems seen today. The Milky Way is part of this ongoing process. It has grown through mergers with smaller galaxies and will continue to change in the future. Its current form is only one stage in a much longer evolution that is still unfolding. The universe itself is expanding, meaning that galaxies are generally moving away from one another over large distances. This expansion affects the way galaxies interact on the larger scales, influencing the overall structure of the cosmic web. Despite this expansion, gravity continues to pull nearby galaxies together. This is why systems like the local group remain bound, even as the universe expands. Within these groups, galaxies continue to interact and evolve. The Milky Way's future interaction with the Andromeda Galaxy is part of this larger pattern. While many galaxies move apart, those that are close enough remain connected by gravity, eventually merging over time. Understanding the Milky Way within this wider context helps explain its place in the universe. It is not unique in its basic structure, but it is unique to us because it is the galaxy we inhabit. The processes that shape the Milky Way are the same processes that shape all galaxies. Star formation, stellar death, gravitational interaction, and the movement of gas all contribute to the evolution of galaxies across the universe. This means that by studying the Milky Way, scientists can learn about galaxies in general. At the same time, by studying distant galaxies, they can gain insight into the past and future of our own galaxy. The scale of the universe extends far beyond the Milky Way. There are billions of galaxies, each containing billions of stars. The total number of stars in the universe is so large that it is difficult to comprehend. Yet within this vastness, patterns emerge. Galaxies form, evolve, and interact in ways that follow the same underlying principles. The Milky Way is part of this larger system, connected to it through the forces that govern the universe, and this matters because it changes how we understand our place in the cosmos. We are not at the center of everything, but part of a much larger structure that extends far beyond what we can see. What happens next is that the universe will continue to evolve. galaxies will keep forming, merging, and changing over time. The Milky Way will follow this path, shaped by the same forces that act across the universe. Even as distances between galaxies increase, the local interactions that define systems like the local group will continue. These interactions will shape the future of the Milky Way and its neighboring galaxies. In this way, the Milky Way is both a self-contained system and part of a much larger whole. It exists within the cosmic web, connected to other galaxies through gravity and the history of the universe. As we look outward, the scale becomes greater with every observation. Each new discovery reveals more of the structure that surrounds us, showing that the Milky Way is only one part of an ever-expanding universe. And within that universe, the same processes continue, shaping galaxies across vast distances, linking them together in a pattern that stretches far beyond what we can fully imagine. The Milky Way has existed for billions of years, evolving slowly through processes that unfold over timescales far beyond human experience. From its earliest beginnings as a collection of forming structures, it has grown into a vast and organized system containing hundreds of billions of stars. Every part of it, from the dense central regions to the distant outer halo, carries a record of that long and continuous history. Our Sun formed relatively late in this timeline, about 4.6 billion years ago, from a cloud of gas and dust that had already been enriched by earlier generations of stars. This means that the materials that make up the Earth and everything on it were shaped long before our solar system came into existence. The elements that form rock, water, and life itself were created inside stars and spread across the galaxy through processes that continue today. As the solar system travels through the Milky Way, it follows a path shaped by gravity, moving steadily around the galactic center. This journey is slow on a human scale, yet constant and unbroken. Over the course of a single orbit, the solar system passes through different regions of the galaxy, each with its own characteristics and conditions. During this motion, the galaxy itself continues to change. Stars are born in dense clouds of gas, live their lives over millions or billions of years, and eventually return material back to the interstellar medium. This material then becomes part of new stars, continuing the cycle that defines the Milky Way. The galaxy is not fixed in its current form. Its spiral pattern shifts gradually, its stars move through the disk, and its outer regions evolve as it interacts with nearby galaxies. Even though these changes occur slowly, they are always taking place, shaping the structure of the Milky Way over time. Observations of the galaxy have become increasingly detailed with advances in technology. Space-based missions have mapped the positions and motions of vast numbers of stars, revealing the structure of the Milky Way with greater clarity than ever before. These measurements allow scientists to trace the paths of stars and understand how the galaxy is organized. By studying the motion of stars, it is possible to reconstruct the history of the Milky Way. Patterns in their movement reveal past mergers, shifts in structure, and the influence of unseen mass. In this way, the galaxy can be read as a record of its own evolution, with each star carrying information about its past. The scale of the Milky Way remains difficult to fully comprehend. Even with detailed maps and measurements, it extends far beyond what can be directly experienced. The distances between stars, the size of the galaxy, and the timescales over which it evolves all lie far outside ordinary human perception. Yet despite this scale, the Milky Way is also the environment in which we exist. Every observation of the night sky is a view from within this system. The stars that can be seen with the eye are only a small fraction of the total, but they provide a connection to the larger structure that surrounds us. The quiet appearance of the night sky can make the galaxy seem still, but it is always in motion. Stars move along their paths, gas flows through the disk, and the entire system rotates steadily. This motion is balanced by gravity, maintaining the overall form of the galaxy while allowing for gradual change. Looking further into the future, the Milky Way will continue to evolve. The predicted interaction with the Andromeda galaxy will reshape both systems, combining them into a single larger galaxy over billions of years. This process will alter the structure of the Milky Way, creating new patterns and redistributing its stars. Even beyond this event, the galaxy will continue to change. Star formation will eventually slow as available gas is used up, and the population of stars will shift toward older and cooler types. Over extremely long timescales, the appearance of the galaxy will become different from what it is today. At the same time, the broader universe will continue to expand. Distant galaxies will move farther away, and the large-scale structure of the universe will evolve. The Milky Way will remain part of this larger system, shaped by both local interactions and the expansion of space itself. The understanding of the Milky Way has grown over time, moving from simple observations of a band of light to detailed studies of its structure and behavior. Each new discovery adds to this understanding, revealing more about how the galaxy formed and how it continues to change. Despite these advances, there is still much that remains unknown. The exact nature of dark matter, the details of the galaxy's formation, and the full complexity of its internal processes are still areas of active research. The Milky Way continues to offer new questions as well as new answers. This matters because it shows that the galaxy is not only a place, but also a subject of ongoing discovery. It is something that can be studied, explored, and understood more deeply over time, revealing its complexity through careful observation and analysis. What happens next is that this process of discovery continues. New instruments, new observations, and new ideas will expand our understanding of the Milky Way, allowing us to see it in ways that were not possible before. Even as this understanding grows, the experience of looking up at the night sky remains the same. The Milky Way appears as a quiet band of light, stretching across the darkness, unchanged in its appearance, even as our knowledge of it deepens. In this way, the galaxy exists on two levels at once. It is both a deeply complex system shaped by physical processes and a simple and familiar presence in the night sky. As the Milky Way continues its slow and steady evolution, it carries with it the history of everything that has taken place within it. Each star, each cloud of gas, and each movement within the galaxy contributes to this ongoing story. And within this vast system, our own existence is part of that story. The atoms that make up our world were formed in earlier stars, and the conditions that allowed life to develop were shaped by the structure of the galaxy itself. The Milky Way is not separate from us. It is the environment that made our existence possible, the system that continues to carry us through space as it evolves over time. As the galaxy moves forward, so do we, traveling along with the sun as it orbits the center. This motion is constant, unbroken, and shared by everything within the Milky Way. And as this quiet journey continues, the galaxy remains a vast and enduring presence, shaped by time, guided by gravity, and filled with processes that continue far beyond what we can see. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about the Milky Way.